So I just want to do a brief recap of the ideas of crystal field theory insofar as they affect our interpretation of UV visible spectra. Sometimes this material is covered in a descriptive inorganic chemistry course. Sometimes it's covered in freshman chemistry. I don't know what you've had or which of you might have had descriptive inorganic, so I'm just going to press on and assume that hardly any of you do. The ideas are pretty simple, and if you remember the essential elements of electronic configurations, sp2d1 configurations, just knowing how the electron count can be distributed among the s and p and d orbitals. This is a great place to start. But I want to focus your attention really on three ideas. One is that transition metal complexes in solution are colored. Not only that, but sometimes they're intensely colored and sometimes they're only faintly colored. So in this picture here, you can see that I picked a selection of transition metals: titanium, chromium, manganese, iron, cobalt, nickel, copper. And what's not shown is scandium. What's also not shown is zinc. And this is because both those complexes are colorless. Scandium by virtue of the fact that it's a D0 complex, and zinc by virtue of the fact that it's D10, and so there's no place for electrons to be excited to, at least among the d orbitals. But just thinking that we'll start by trying to explain what color is. The next thing we'll try to explain is why is it that manganese is so faintly colored while things like cobalt and copper are more intensely colored? What's unique about those? What's different about manganese? And the third thing I want to set up is, here's two examples: cobalt hexafluoride. So hexafluorocobaltate, which is cobalt with 6 fluoride ions and a -3 charge, is an octahedral complex. And hexacyanocobaltate is also an octahedral complex with 1 cobalt and 6 cyanides and a 3- charge. They're both D6 for reasons that I'll get into. But while the fluoride complex is paramagnetic, the cyanide complex is diamagnetic. Despite the fact that they're both octahedral, they both have -1 ligands, they have the same d electron count. What's going on here? How can we explain this? And I'm happy to report that modern crystal field theory incorporates all these three ideas. So let's get right to it. Going to the next slide. The first avenue for discussion is, what is color and how does what we see relate to what is absorbed? The simplest way to explain this is with basically a little color wheel. If I divide the spectrum into 6 colors, try and draw a reasonable pizza, I can label these as red, orange, yellow, green, blue, violet. And what's interesting is there's a complementarity between the color that you see and the color that's absorbed. In other words, if we observe a complex that has a red color, that means it must absorb its complement. In other words, it must absorb green. Likewise, if a complex appears violet, that means it must have absorbed in the yellow region, because if we look at the whole spectrum, red, orange, yellow, green, blue, violet, if you take away one color, the other complementary color simply dominates what you see left. So we'll pick that point up again in a little bit, but what we're trying to explain is, how is it that some particular colors are removed from the spectrum by transition metals? So we've covered what I would consider item 1. Item 2, what is the d electron configuration of the transition metal in a complex? So let's say we're talking about copper +2. If you look at the position of copper in the periodic table, you'd say that copper was 4s2 3d9. Copper is the 9th element in from the left among the transition series, and to make a copper 2 complex, we have to take away 2 electrons, and the reason why we take them away from the s is because the 4s is higher than 3d. The truth is more complicated than that, but let's just go with that for now. We take away the s electrons first, and then If we have to achieve any higher charge, then we can take some electrons away from the d set. So what we get now is copper plus 2 is basically 3d9. In other words, copper has 9 valence electrons to work with, and all the color must somehow be attributed to those 9 d electrons. The next thing is, how might we, let me do one more example briefly. So let's look at another one, manganese plus 2. We start with manganese. Manganese is 4s2, 3d5. We take away 2 electrons, we get 3d5. In other words, whatever valence electrons remain after you've accounted for charge, they become d electrons. So these are all examples of complexes, like in the case of copper plus 2. All the species that are shown in the previous slide are all examples of octahedral hexa-aqua complexes. That is to say, the metal ion is in the center of an octahedron. It has a total of 6 ligands at 90-degree angles, where the ligands contribute a pair of electrons to the metal ion. In the case of water, one of the oxygen lone pairs would be covalently bound to the copper, and the other one would not really play a significant role. So the third question is, how might this relate to transition metal complexes with ligands other than water? So here's a couple we can draw. So let's see, cobalt hexafluoride has 6 fluorides bound to it. It has a net -3 charge. Each of the fluorides is -1. To get a -3 charge and have 6 -1 ligands, we have to have cobalt plus 3. In other words, this must be a D6 complex. In other words, use the charge of the ligands to figure out what the charge of the metal ion must be. Use the charge of the ligands to find out what the charge of the metal ion must be, and once you know the charge of the metal ion, you can work out the d electron configuration. And this is true for situations where you have a mixture of different kinds of ligands. So here's another, maybe slightly more esoteric one. Tungsten monooxo tetrachloride is a square pyramidal complex. Oxo has a -2 charge. Chloride has a -1 charge. And since there's 4 chlorides, that means we must have tungsten plus 6, and tungsten plus 6 is D0. So that's electron configurations, at least d electron configurations in a nutshell. You figure out the charge of the metal ion. You subtract the correct number of electrons from the total valence electrons to find out how many d electrons remain. The next question is, how are the d orbitals affected by the ligands? So to answer this question, we have to remember that some of the d orbitals point in the direction of the ligands, and some of the d orbitals point away from the ligands. So which ones do we have? We have d xy, d xz, and d yz, and then we have dz squared and dx squared minus y squared. Now it turns out that we can roughly divide these sets of d orbitals into 2 groups. These guys, this group of 3, points away from the x and y and z axes, while this group of 2 points at the x and y and z axes. It's really that simple. The dz squared orbital, you might recall, looks like a p orbital, but it has the donut in the equatorial plane. The dx squared minus y squared is a big d orbital that lies along the x and y axes, where we have opposite phases in each direction. So the z squared and the x squared minus y squared belong to what's called a doubly degenerate set. And in using the labels of group theory, we would call these the EG orbitals. The G comes about from the fact that the d orbitals have a center of symmetry. That is, if you invert them through the center, you get the same orbital back. And the E label refers to the fact that they move in pairs. So the dz squared and the dx squared minus y squared constitute the two components of an EG set of orbitals. On the other hand, the xy, xz, and yz are known as the T2G orbitals, and where the T illustrates the fact that there are three orbitals in this set, and the 2G are just another label, but the G part again tells you that the orbital has a center, has the center of symmetry. So we have two orbitals, two sets of orbitals, one of which points at the ligands and one of which points away. So we can start by asking the question, how are they affected by the ligands? We have a set of 5 degenerate orbitals. And then we ask how they're affected by a spherical field, and we would say that in a spherical field, all the d orbital energies go up because of electron repulsion. And then we divide the orbitals into what happens when they are split into let me put it another way. The x squared minus y squared and the z squared orbitals point at the ligands, and so in an octahedral field, we have two orbitals that are actually higher in energy and 3 orbitals that are actually lower in energy. And we call these the T2G and these the EG, and the separation between the T2G and the EG is known as delta O, or the octahedral crystal field splitting. So, to recap, because the d orbitals are in different spatial relationships with respect to the ligands, some of the d orbitals go higher in energy and some of the d orbitals go lower in energy. And the extent to which we differentiate between the two is known as delta O, or the octahedral crystal field splitting energy. So now we can say, I'll address the point, sort of what is color over here. And let's take a simple example, titanium plus 3. As an octahedral complex, it turns out this would be a D1 complex if the d orbitals are split such that 2 orbitals go up in energy and 3 are lower in energy. We'd call this delta O. We'd put 1 electron in the T2G set, 1 electron in the EG set. Now, if the right photon comes along, such that the energy of the photon is equal to the crystal field splitting energy, then we would promote that electron, and we'd get a new configuration that I'll sketch over here, where the electron is now in the EG orbital instead of the T2G. So the catch is that not all of the delta O's, not all the splitting energies are the same. Some ligands split the d orbitals significantly. Some ligands don't split the d orbitals at all, or very much. And the example of hexafluorocobalt and hexafluorocyanide, or hexacyanocobalt, are good illustrators of this. Fluoride is known as a weak field ligand, and cyanide is known as a strong field ligand. And what that means is that while the d orbitals in hexafluorocobalt are split, the splitting is really small. So delta O is really kind of relatively small. Whereas in the hexacyanocobalt complex, that splitting energy is really big. So delta O is big. So if we try to fill these energy diagrams with electrons, in both cases they're d6. And so we can start by putting in 3 electrons into the T2G orbitals in both cases. Now we've used up 3 electrons, but we have 3 more to go. So it turns out in the case of F-, delta O is less than the pairing energy. That is to say, the electrons would rather go into different d orbitals than pair up. So the 5 electrons go into different d orbitals. We get the 6th electron, which puts one more in the T2G set. But this gives us something called the high spin configuration, because we have more unpaired electrons than we necessarily need to have. On the other hand, in the case of the hexacyano-cobalt complex, delta O is bigger than the pairing energy. That is to say, it's energetically less costly to put the electrons, all the electrons, in the T2G orbitals than to try to put them in the EG set. So all the electrons go in spin paired in the bottom. This is known as the low spin configuration. And right away we can see that hexafluorocobalt 3- is paramagnetic because it has unpaired electrons, while hexacyano-cobalt 3- is diamagnetic because it has all paired electrons. And this illustrates the fact that ligands have different strengths. Ligands have different capacities to cause the d, x, y, xz, and yz to separate from the dz squared and the dx squared minus y squared. And this gives the example of high and low spin configurations. So with this, we can answer a couple critical questions. I think I've already got the hexafluoro 3- and hexacyano 3- question sorted out. But one question is, why is manganese plus 2, or hexaquamanganese plus 2, I'll just draw the formula out, MnH2O 6 2+. This is an octahedral manganese complex. It has a +2 charge, so therefore it's D5. Now it turns out that water is a relatively weak field ligand. And so the splitting energy, delta O, is relatively small, delta O less than the pairing energy. And so my 5d electrons go into different orbitals, or different orbital sets, T2G down here and EG up here. And so this means that if the right photon comes along, or at least if the right energy photon comes along, all the spins of the electrons are the same. They're all spin plus 1/2. And so in order for us to see a transition, in order for us to promote an electron from a T2G to an EG set, we have to flip the spin. And the only way to do that is the sort of illegal thing of taking an electron out of the T2G and forcing it to flip and pair up with an EG orbital. This is a spin-forbidden transition, and it explains the fact that the extinction coefficient for manganese is typically less than 1. 0.01 is pretty common for situations like this. Another good example is zinc plus 2. Zinc plus 2 turns out to be colorless. I'm just going to quickly draw the configuration. Because it's zinc 2, we would say this is a D10 complex. And to put the electrons in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is delta O. And the catch is that a photon might come along, but there's no place for a lower electron to go to get into an EG orbital. There's no room in the N. There's no allowed transition because there's no vacancies. So I finally covered the magnetic properties. I've covered where color comes from. I've covered high spin, low spin. If you have questions, please feel free to drop me a line, and I'll see you in class.